The big advantage to this, to me, is it's just so easy to create a multitask application. If you have an array and you want to spawn one thread, like you'd like to apply the rank operator, but you'd like to use a different thread for each item, then just create a task with a rank of whatever the item rank is, and it'll automatically run in multiple threads. You don't have to do anything more than that.
Welcome to another episode of ArrayCast. I'm your host, Connor, and today with us we have a repeat guest, I think setting the record for the third appearance on ArrayCast. But before we introduce him, we will go around and do brief introductions from our three panelists today. We'll start with Bob, then go to Adam, and then go to Marshall.
I'm Bob Therriault, and appropriately today, I am a J enthusiast.
I'm Adám Brudzewsky. I definitely am intrigued by J, but I do APL.
I'm Marshall Lockbaum. I started out with J. I worked for Dyalog for a while, and now I develop BQN.
And as mentioned before, my name is Connor. I'm a research scientist at NVIDIA and programming language polyglot, but I have a huge passion and enthusiasm for all array languages. And with that said, I think we've got a couple announcements. We'll go one from Bob, and then the last one's from Adam, I think.
My announcement is a podcast called Technium that I hadn't heard of before, and they're on YouTube as well. Two guys, and they're pretty well informed about programming and developing and things like that. But they take a look at APL, and I think of them kind of as the chat GPT of looking at APL, because it's an outsider's view and they've done some research, but they do get some things wrong. So don't take everything they do for gospel. They actually do mention this podcast, but in a way that I'm not sure whether I take as a compliment, because they say that just shows you how far out these guys get. It's kind of niche.
I mean, interestingly, the title of their episode is factually wrong. You need a special keyboard to code in this language, APL.
Oh, yeah.
I don't use a special keyboard for APL.
That probably is like the number one comment I get on videos and stuff or like tweets. It's just, how do you even type this? And I'm just like, there is literally like half the population of the world types and texts in a non-like Arabic based alphabet. Arabic? I pronounced that word wrong.
Non-Latin, you mean?
Non-Latin, right.
Well, it's also true for Arabic.
Yes, it's true for both, yeah.
And it's like, there's how many people that type, Mandarin Chinese? I don't know, close to like 1.5 billion or 2 billion. And anyways, it's just sort of comical that there's this very Western sort of point of view that like, oh my God, if it's not A through Z, it must be so difficult to type. And it's really not the case.
Well, and of course, the basic characters such as the ampersand and @ sign, which, everybody should take for granted.
Well, and just to give you an example for this podcast, they keep referring to notation as a tool for thought.
Oh, yeah.
And so it's, it's a small thing, but it's those kind of things. They're just missing by a bit.
Actually, there's a Canadian alphabet for Canadian Aboriginal Syllabics. Looks a lot like BQN.
Really?
The font support is not good enough. I would use some of those characters if I could. And also, I don't like to use scripts because fonts render scripts differently from symbols a lot of the time. Like they handle the strokes in a different way. So
sure looks like BQN though.
All right. My list of things to do is going to be listen to this episode, and maybe we'll have we'll respond. Maybe we should all listen to it for next time, and we'll do a little mini response. Anyways, let's go to Adam for the final announcement.
Yeah, the APL Show with Richard Park. We've released another episode. Yay. Go listen to that. We're talking about something really exciting, which is like primitives.
Yeah, I just listened yesterday. I have to be honest. I still don't know if I understand the difference between structural under and what's the other one? Mathematical under?
Mathematical or computational under. Maybe we should do an episode just on that.
Yeah. I think, actually, I don't know. I listened to it. It was great. Structural under is fantastic because BQN has it. I assume Jay. I guess we can actually wait.
No,
perfect way to introduce our guest here. So our guest, if you haven't deduced by the number of times he's appeared, is Henry Rich. He was on episode 6. So our first guest, because even though it was episode 6, the first 5 we didn't have any guests. So our first guest, and he was also on episode 18, I believe, where he was doing something similar. He was he came on to update us on sort of J. So if you haven't listened to either of those episodes, Henry Rich is, I don't know if you want to call him the resident sort of keeper of the J source code, and sort of took over a lot of the work and has done a ton of work over the, I don't know how many past years. So definitely go back. If you haven't listened to that episode, go listen to episode 6, then episode 18 if you want as well, and then come back, unpause this episode, and you'll be a lot more informed. And I think today we're primarily going to be talking about not J9.4, because the last time he was on, we were talking about 9.03. We're going to be talking about J9.4, which is maybe where we should start. Although I realized I was asking something about J, and then I said that's a perfect time to bring Henry on, and then I completely forgot.
Structural under.
Oh, right, under. So I'm not sure if you want to introduce 9.4 or talk about under for a sec first. Kind of messed that up, but you go ahead.
Well, I don't know what structural under is, so my contribution to that is
Skip over that one.
pretty quick. Is that something that I should do, Marshall?
The thing with both J and Dyalog is that they've done some stuff with mathematical under that does not quite jive with structural under. So it's much more difficult to do it in J than in a new language.
That's only computational mathematical under. But it's time to add ampersand : :
Yeah, that's not a terrible idea.
Well, it could be. If I still don't have any idea what structural under does, so I can't really talk about it.
Well, we've talked about under a little bit here, so maybe we should take a couple minutes, if for those that aren't listeners to APL Show. What does the under in J currently do, the computational under?
The concept of under is it's a change of point of view. You have two verbs, U and V, and you're given an argument, and it's like a similarity transformation in physics. You apply V to the argument, which presumably converts the argument into some space that you can understand. So you apply V, then you apply U, and then you apply the inverse of V to the result of U, which takes the result back into the original space of the argument. The most common usage is under open, where open unboxes an argument.
Right.
So I have some argument. I want to take the box away, do something to it, and put the box back. That's under open.
Right.
The concept applies to any verb V. It might be a matrix transformation, or basically anything that has an inverse is applicable as the V argument.
Taking it into the real world, I always think of anesthesia and operations. You put the person to sleep, you do the operation, and then you wake them up. You want to do that in the right order.
That is an example that came up on the APL Show episode.
I think that was one of Iverson's that he used. I know Roger promoted that too, but I think it was Ken's originally, Ken Iverson's.
And is there from either Marshall or Adam,
I'll go for it,
60-second or less explanation of the difference between structural under and computational / mathematical under? If not, we can just kick it to another episode.
So the geometrical transformation perspective on computational under works really well for structural under too. The idea with structural under is you still have two functions, U and V is this transformation. But here, V is a structural function, so it's not allowed to like add numbers or anything. It just pulls out part of the argument. So one thing, actually open is an example. Like you might say under first. That would be the kind of structural version of the under open thing. So you'd say under first, pull out the first element, and then U applies to that, whatever the result of V is. That part of the argument, or maybe it's reversed or transposed or shuffled around in some way. And then structural under puts that back. So the big difference with structural under is that it works even if V loses information. So this under first thing, you just take out the first element of your argument. That loses all the other elements. So you can't possibly invert that function. But what structural under does is to kind of put the results back where they were in the original argument. So it remembers that information and it gets it back.
So does this mean that structural under is a superset of computational under?
Not
No.
really. There is an intersection that I call invertible under. So if V is a strictly invertible function, like minus or reverse or something like that, where you can always undo it exactly.
Yeah.
then that can be actually under reverse is both a structural and a computational under. So it's invertible. They both do the same thing. But computational under also does some stuff like, well, at least in J and APL and BQN sometimes, the inverse is not always exact. So it'll do things like if you want to invert the square function, which is really nice because you can take like the magnitude of a vector with summing under the square. So it'll do square, sum, square root. It has two options for the inverse of the square. There's the positive and the negative square root, or generally one number and it's negative. So it chooses one of those. And structural under never does that. It never makes that choice. So in that way, computational under is not exactly compatible.
Henry, you were going to say something?
Yeah. In J, we can emulate structural under take the case that Marshall mentioned, just operate on the first. The way we do it is we define a verb to use for V. The verb itself selects the first argument, the first item, and its inverse would be defined as storing into the first item. Whereas taking the first item itself doesn't really have an inverse. If we know that what we're trying to do is modify the first item, we can create a verb that has a defined inverse, and that would provide exactly the structural feature that Marshall was talking about.
How would that work? I don't understand. It's lossy. As soon as you take the first element, you've lost information about the rest of the array.
Okay, I see what you mean.
And another example would be under raise or enlist or ravel or anything that destroys the structure.
Yeah, you're right. You'd have to make it more complicated. The verb would have to carry the argument along. Okay. I take back everything I said.
There's an adverb in J called amend, right? Or something like that. And
yeah, so that allows you to put elements into an array. But the thing about structural under that it doesn't do is structural under works at like all levels and stuff. So you can take the first element of the first element. You can take the first element of each element.
Right, so it's a superset of amend.
Yeah.
Right. It can not only can it dig into any part and any structural transformation of the main argument, it also has the ability to apply a function there rather than just replace elements there. So amend this as sub.
Well, amend does that also. Amend has a gerund form where you can specify the selector and the modifier and the thing to be modified. So yeah, for the particular case of first, you could use that amend, but that would not be it wouldn't generalize to things other than just amending an array.
And Dyalog APL has also an at operator, and the structural under is a very powerful superset of the at operator. At operator can do exactly two things that the under can do, but it can do so much more.
Well, there are more than one things it can do with the select half of that. Like it's really hard to figure out how to do it, but it can do reach indexing and stuff like that.
Yeah, okay, but the at operator can either index into an array and make changes there, either with function application or substitution, or it can apply a Boolean mask to an array and use that to either do substitution or function application. But that's it. And the under can take an operand that selects or masks, in which case it has the same functionality. But it can do anything. It could have an operand that does all kinds of things. So you can use a composite operand that reverses and drops some elements and then takes some elements and then selects the third one of those, right? And then changes something, and then it all unrolls back to where it came from.
All right, maybe we should do a whole episode on under, at, amend in J. I gotta say, at in Dyalog APL is something that I find extremely not ergonomic, and anytime I try to use it, the first way I try, it doesn't work, and I have to put something in a defun or anyways, but it is one of the most, I think, when you we mentioned tool for thought. Now I'm saying it wrong. A tool of thought. Geez, Bob, we blame Technium. That's right. Marshall, get over there and get rid of those.
I hope those guys listen to this episode.
Yeah. Oh man, I hope that would be great. I had some. There's a guy on YouTube called Primogen who's like a Rust YouTube channel, and he Twitch streams. Someone just sent me a video 2 days ago or yesterday of him watching and like critiquing one of my videos, and he's a bit crude. The jokes sometimes he makes are maybe not suitable for work, but he hates C++. And I was just killing myself laughing. So like, if anyone out there wants to do, a review of these niche developers that are, off in, cuckoo land, I find that stuff, I don't take it to heart. Someone said, oh, you're going to be upset when you watch this. And like 3 minutes in, I was like pausing the video and like killing myself laughing. Anyways, all right, let's get to the actual topic that we brought Henry to talk about today, which is the new release of J9.4 or 9.4. Maybe we'll start there, and you can talk to us about this switch up, if you will.
Switch up? What?
The numbering. We went from 903.
Oh, the numbering. Well, okay. Yeah, heretofore, J started out J1, J2, J3 up to J7. That was 25 years ago, and then it reset to J2.01, I think, or 201, and continued on with that numbering scheme up until 903. And now Rick Sherlock has done the work to let the Windows procedure WinGet, I think it is. I don't actually know, but it's something distributed from Microsoft that will let the Windows executables be distributed by a trusted source. So that's good. And they use a different numbering system. So we decided we would switch to that. So the new release is now J9.4.1. The betas are 9.4.0. And so it's being released under that numbering system. So it used to be J9.04, now it's J9.4.1. 9.4 is a major release, and this is one of the biggest releases we've had in a long time as far as functionality. And with this release, finally, J becomes multi-threaded.
Ooh.
With full support for multi-threading. This owes a lot to Elijah Stone, who did a great deal of the work. But the idea is you have a verb that'll create a thread. You create as many threads as you want. Usually one thread per core is about right. But you might have an application where, say you're listening on a whole bunch of sockets. You might want to have one thread per socket. That's really not a very efficient way to do it, but it would save you from rewriting your socket code. You create the thread. Once you've got the thread, then you can use it by, you take your verb, let's call it you, and there's a new conjunction, T dot, and you say you, T dot, whatever the argument, zero, and that just runs your verb as a task. It runs your verb in a thread. You don't have to do anything beyond that. The result will come back in a box, and when you look at it, you'll see the result. And the result's always there. It's magic. Of course, what happens is if your spawning task looks at the result before it's actually finished, the task will block until the result is available. But you can spawn as many tasks as you like, and then wait for them later. You can wait for them. You can probe them to see if they have a result yet, and avoid having your main thread wait. The big advantage to this, to me, is it's just so easy to create a multitask application. Like if you have an array and you want to spawn one thread, like you'd like to apply the rank operator, but you'd like to use a different thread for each item, then just create a task with a rank of whatever the item rank is, and it'll automatically run in multiple threads. You don't have to do anything more than that. So if you're trying to, if you wonder whether your application could benefit from multi-threading, it's really easy to find out. Just try it with tasks and see if you get a performance increase.
So this means, it sounds like all of the multi-threading is on the user to encode. You're not going to expect, some heuristic of we're doing some reduction on some massive array, and then behind the scenes it knows it'll be more efficient if it launches a few threads. Nothing like that'll happen. But if you want to sort of program it in or test something out or write maybe a multi-threaded reduction, that's something that is going to be quite easy for the J developer now with 9.4.1 at least.
Well, that's true. It would be very easy, but it's not true that threads are only used when the user asks for them. For verbs where we know for a fact that multi-threading is going to be advantageous, and the prime example of that is matrix multiplication. Mm-hmm. If we know threading is going to be an advantage, we will. So to take that example, matrix multiplication, we automatically run the matrix multiplication on as many threads as you have defined. To get a little deeper, you can define threads in thread pools, and thread pool 0 is the default pool, and it's the one that the system will use to do things that it thinks will be better done in threads. So far, matrix multiplication and some custom functions that we've written are the only ones that we've automatically tasked, but reduction would certainly be a good candidate for that, and sorting too, maybe. As we identify those cases, we'll code them up so that they'll multi-thread automatically. Yes, we already do that for matrix multiplication.
Does that include the matrix division and inversion?
No, just matrix multiply. Although, well,
so division uses matrix multiply under the covers, doesn't it?
Yeah, in the J implementation, division is done by repetitive multiplication, so that would speed up. Although really, LAPACK is faster for inversion. But if you had to invert a rational matrix or something, you would benefit from the multi-threading for that. There are a lot of things that don't benefit from multi-threading. To get benefit from multi-threading, you need to have a high proportion of computation to data movement in and out. If like adding two vectors, it's not going to help to try to do that in multiple threads. Reduction, on the other hand, you probably could benefit from doing in multiple threads, and we'll get to that.
But that's dangerous, right? Because if you're doing reduction that's computational, say a plus reduction, then you will get different results.
Well, that's true. You have to be willing to accept irregular floating point round off. That's true even if you're adding in a single thread, right? I mean, when you decide, well, I'll use AVX2 instructions and add in with 4 accumulators at a time, well, now you're going to get different results than if you added one at a time. And AVX 512 is going to get still different results. If you really care about the accuracy of reduction, we offer a high precision reduction that has predictable round off and operates at essentially quad precision for the accumulation. But I think most users are content to let it round off as the machine chooses to. An important feature of our threading implementation is that all the threads share the same J namespace. So I have seen languages that said, well, we'll support multi-threading, but the address spaces of all the threads are separate. They can't talk to each other. That's supporting multi-threading, that's true, but what the user really wants is to be able to apply all the threads on the same problem at the same time. And to do that, you really need to have the threads share the same space for names and variables, globals, verbs, everything. So we do that. So that's one of the things that makes it easy to try out an application and see how it benefits from threading, because you just say, well, here's my verb, run it in multiple tasks, and that verb will be automatically shared.
So how does that even work? And since these are OS threads, not green threads. So I thought every processor thread had to have its own memory. And how can they even share them?
No, they share memory space.
And so that means you could have two parallel threads that that both modify a global variable and they can see each other's changes in real time?
Yes. That's good and bad, right?
So there are performance effects if you're hitting the same memory, but the processor does make sure you get consistent results.
Well, the processor doesn't. I had to. The program, because it was quite a rewrite of the way the interpreter deals with names.
Yeah.
Well, I mean, the thing is, when you have multiple threads and they can all modify the same names, you realize that your concept of a symbol table almost goes by the board. Thread A may read a name, and thread B in the next nanosecond erases that name.
Yeah, I didn't mean like high level consistency. I know you have to put that in, but I meant the multiple CPUs can all access the same memory, and it's nothing crazy and undefined happens.
Right, but it was very subtle to make sure that the programs still work even when names can be erased instantly.
Or the values change, right? What happens if...
No, the value doesn't change. If thread A accesses a variable X and thread B immediately writes to X, thread A will continue to run using the value that was in X.
Oh, wow.
The point is here that the value has its own existence separate from the symbol table. So A will continue to run, B will overwrite X, and you could say probably you're in for something bad to happen there, but not necessarily. I mean, let's say the variable X, maybe I'm doing some alpha beta pruning in a game. I'm trying to find the best results so far, and X might just be the best value that any thread has found, and I'm content with using an old value as long as the value correctly represents the current state of the game. So for that, you need semantics above the level of the hardware, as Marshall was saying. The hardware will make sure, or the hardware and the interpreter will make sure that you don't go off and access undefined memory. But you need a level of semantics above to make sure that if two threads are modifying a shared variable, they need to be able to lock it so that the right one modifies it. And so there's a set of concurrency primitives that allow that semantics for the threads to be accessed at the same memory. But where it's really easy, what it makes easy, I have tried on several occasions to run multitasked programs in J by starting a new instance of the J interpreter. And it's always just a pain to share all the data. You have to send the data from some central task to the other task. It operates on it, comes back. So somehow there has to be something that knows what is everything that has to be sent from task A to task B and what has to be gathered as a result. All that goes away. You just start tasks A, B, and C, and they look at whatever global names they need to look at. They get the current values. And as long as they're not modified, they don't have to worry about it. If they modify something, maybe they need to worry about it. But it's really easy, makes it easy to start a multi-threaded application.
And the sending of that information back and forth, that takes up a lot of time and energy, right?
Well, it takes some time. Yeah, it takes time to copy words from one thread to another. What happens is you share out the computation among tasks A, B, and C, and each one of them finishes their result, and they put the result in a box and send the box back. So what returns into the result area, the result's called a PIX. That's a word for a special kind of box. The PIX is the magic box that whenever you open it, it's got what you're looking for in it. But by waiting until the result's there. The tasks return their PIXs, which point to the data. Okay, so now let's say the main thread wants to look at the values. So it opens a PIX. It says, there it is. There's my data. And here's the pointer to it. So far, there hasn't been anything, nothing has slowed down. But when the thread wants to go use that data, it finds that it's over in another task. It's in a different core. It's in level 3 cache somewhere, and it has to be brought back in as if from level 3 cache. And that's where the time is spent. So that there's time spent transferring the data to the task and transferring it back. But that overhead is only as big as the arguments in the result. So the key to making a good task definition is do enough computation on the data that the computation takes more time than the transfer. If you do something that touches the data a dozen times in the thread, like say sort it maybe, that'll be a good trade-off. Having the data operated on in fast cache in another task will be worth the data transfer. Not adding 2 vectors. That would be dominated by the data transfer time.
And that's because the work that you do before the PIX is provided or the information comes to the PIX, the more work that's done there, the less transfers you have to do back and forth between PIXs.
Yeah, well, the more work you've done, you get the advantage of having multiple processes, right? If I do 100 things, or if I have 1,000 things to do, and I can split them among 10 processors, great. That's only 100 per processor. And if the data transfer time amounts to only 1 or 2, that's a good trade. I get the job done in 110 units of work instead of 1,000.
But the problem is that the processors today are so fast compared to the memory, which is so relatively slow, that a lot of the work that we want to do happens at memory write speed and memory read speed. So that you can never get any speed up by sending the data somewhere else, because you need the data back again. And that transfer takes the same time as just computing it over here, right?
So one advantage of using multiple cores is that each core has its own cache. And that actually speeds up your memory usage if you can keep each core, in its own contained space that's running on its own. I think that's actually one of the really big advantages of splitting stuff across cores.
Yes. Well, and there's another. This is something I cannot find much information on. So maybe some of you guys know. I take an Intel processor. The level 3 cache is there's a little bit of level 3 cache with every core. So it's the level 1 and level 2 are directly tied to the core, but the level 3 caches in effect are in parallel, so that the bandwidth to level 3 cache is pretty high. The level 3 cache is itself fairly slow, and there's a limit to how much one core can get from it. But multiple cores could get the same level of bandwidth each that the individual core can get, because those caches are actually running in parallel, even though the data is shared among the different cores. Each cache has pretty fast access to it. And in that case, there is a benefit. Even if you have to transfer the data through level 3 cache, there's a benefit from having multiple cores working on it.
Because they can all be doing it at the same time. Yeah,
because the cores work in parallel. The memory held by level 3 is not contiguous. The addresses are permuted so that any access to level 3 essentially goes to a random level 3 block, allowing many level 3 blocks at a time to share data over the ring interconnect. So the CPU designers have helped us out here. I think multi-threading really is going to be an advantage for a lot of things. You just have to, I think usually you want to have an explicit verb that you can, something that's several lines long, run that in parallel, or a large tacit function. But something that accesses the data a few dozen times, that's going to benefit from being in a task.
And working in J, do I have to do anything to kick that in? Like, do I have to specify how many threads I want to work first, or is it just going to kick in automatically?
Yeah, we've deliberated over whether we should make this automatic for the user, but the idea would be somewhere in your startup file, you would say, I want to create 10 threads. And you would create the 10 threads. And from that point on, they're available for use in tasks.
And you were saying a thread per core is probably optimal. Is there any particular reason for that?
Well, if most J primitives I can use all the bandwidth available to a single core. So there's not a whole lot of advantage in having two of them running on a core. It might be possible, but they're going to have less cache each.
You're talking about hyperthreading here?
No, I haven't measured it, but I don't see that. Like if you add two vectors, I will take all the bandwidth that the caches can provide with a single core. I just don't see that hyperthreading is going to help much.
Yeah.
And I don't do very many mispredicted branches. I guess we say that's a topic for exploration. My best guess is that one task per core is going to be the right number. It will depend on the task to some degree.
Well, we don't think about it too much inside the array community, but I'd like to ask about the impact that using immutable arrays instead of mutable arrays has on this.
I don't have any immutable arrays, really. Once an array has been referred to twice, I guess you could say then it's immutable. Is that what you're thinking of?
Yeah, well, the semantics are immutable.
Well,
All the array languages are like that, right? Everything is passed by value. So everything appears to be immutable. You can just create a new array that's similar or identical to the old one. But underneath the covers, every implementation keeps track, right, of reference counting.
Well, and yeah, I mean, the only way to know is to have another copy of that array lying around and see if it changes. And given that it doesn't, the arrays are, I would say that's immutable semantics for arrays.
Yes, immutable semantics, but it's very important not to actually implement immutable arrays. I've gone to some trouble when two arguments go into a primitive, they're not referred to more than once. I'll delete them as soon as the primitive completes. So you need to do that to share the memory so that you keep the cache footprint low.
Yeah.
And also you need to implement, if you're adding two arrays and if you can add them in place, that's much faster than, a two address addition is much faster than a three address addition. So there's involved in deciding when it's okay to reuse one of these semantically immutable arrays.
Yeah, true. I mean, but on the other hand, you're not dealing with a situation where two threads could simultaneously modify the same array. I mean, that seems like a pretty big deal to me.
You're saying that they cannot modify the same array? Yes, that's true. If you do that,
yeah,
they can in a limited sense if the arrays you're talking about are pieces of an array, like you have to execute different tasks on different sections using the rank operator. So you create a task for every section, then the individual sections would be recognized as being reusable. But in general, you're right.
So this is only if the original array is cut into sections and then not referenced,
right?
Deleted,
yeah.
I guess. Yeah,
that happens a lot, though. That you have just a sentence. The result of every verb is not referenced unless it's assigned to something
or further used in the expression. Right?
Well,
it stays at ref count 1 unless there's an assignment.
Yeah, it stays at ref count 1. So if it goes into a fork, I can't modify it on the right side, but I can modify it on the left side if I know that.
Oh, because we're not going back towards the right.
Yeah, we're not going back to the right. So keep track of all that and retire the arrays as soon as they're not needed so that their cache space can be brought back. Jay has done that for a long time. But in these tasks, I suspect that the main thing is going to be explicit definitions that run on local variables. And those are not, local names in J are not visible to anything else. And there the tasks will be completely separate. And reading from a shared global, there's no problem with that. If two threads wanted to write to the same global array, that's a problem. That's not a problem, but
it's a performance problem.
It's a performance issue, right? So, how would that work? Well, actually, if they locked the array before they modified it, each one of them would be able to operate on it in place. So that, yeah, two tasks needed to do that would need to use the locking primitives to guarantee that there's no simultaneous access to the name. And in that case, they would not have to copy the array.
So so these pixes, they're futures, right?
Yes.
It's just basically a promise that in here there will be a value in the future, and at some point.
Right.
And then, but if I understand it right, they are boxes. So you said that in order to test your code with parallelism on the computation, you just stick that T dot in it. But this actually changes the result value, right? Because now everything you get back is boxed, and you need to unbox it.
Yeah, you have to unbox it. The T dot operator is defined as applying you and then boxing the result. So if you want to be compatible, you would arrange to have your original verb produce a boxed result and open it. That's cheap.
So it's equivalent to
Box atop you, yes.
box, but running, yeah, box atop whatever you're doing.
Yeah, but that means you can, by having the futures in a pix, you can pass the pix to another verb. You can do anything with it that you would do with any other box, and you don't have to wait for the result until you actually look inside.
And pixes are atomic the same way boxes are, right?
Well, there are boxes,
Yeah.
right?
Maybe they are boxes, yeah.
Yeah, pix is a form of a box, right?
That must give some interesting effects then. If you, let's say we have an array and you're using, I don't know how you read this, the T dot. Does it have a name?
Yes, task.
Execute as task. So if you say my function task rank something, whatever, rank -1, you apply it on the major cells, then you get a list back, a vector.
Right, a list of pixes.
So the overall information about the rank of the result is temporarily lost until you do an unbox rank 0, right?
Right. You would
Well, you can just use unbox.
Oh, okay, right.
Well, but I might not. I could just, if I expect that the results of the individual boxes are conformable, then I could open the whole thing. But I might just want to look at one box and see what its result is.
But yeah, if they don't conform by the time, but when you open them all up, then
I mean, it's not an error unless
but you pad. I don't know how J works on this thing. If you unbox something,
yes, it would pad. But if one of them is numeric and the other is character, you take an error.
You get an error at that point.
Yeah, I'm not quite. I think I've diverted you from your point. What? So yes, you get a list of pixels.
Yeah, it's just that's starting me. It's something we're thinking about, talking about it at Dyalog. We haven't implemented as a primitive yet, but we have models that behave like primitives for running parallel in OS threads. We already have a primitive running green threads, but we haven't. I don't think anybody has suggested changing the structure like that, which is why running it with rank is not going to work well, because as soon as the result comes back, as soon as we want to pass on the results further, then you would have to await everything. Otherwise, you cannot know anything about the result. We don't know what rank it has.
Well, if you stick it in a box, you don't have that problem. That's why I did that.
Exactly, but sticking it in a box effectively changes rank into an each, even though each isn't a primitive in J, but each is really just rank 0 under.
Well, it's under box rank 0, which in J you kind of get implicitly.
Yeah.
So we've only been doing it so that it has value for each, and that's really what's happening in J as well. Except we also do the whole unboxing transparently, whereas in J you'd have to be explicit about the unboxing.
Right. Yeah, I don't see that as a problem. But yeah, that is true.
Well, it just means that you actually in with the proposal we have in Dialog, you can actually add this parallelism operator and expect everything else to work the same. You can't detect a difference in value.
Well, Dialog also has the problem that because it's got this floating array model, characters and numbers sort of leak out of boxes. So
yes, it wouldn't work anyway to try to box up things.
that is a significant implementation issue, I guess.
Yeah.
It's not impossible to support, but
no, I'm just contrasting them because we very much see a Dialog other array language implementations as beneficial to us because they'll go off and try various things out, and then we'll be the slow ones to learn the lessons. 10, 15 years later, we implement something similar but better because we know the mistakes everybody else made.
I think we waited a long time for this in J, so we benefited from some other people's mistakes too.
Everybody's sitting around waiting for someone else to do it.
Exactly.
The one thing we did do, this was Elijah Stone's push, was we use futexes rather than mutexes for the synchronization operator, and that's a subtle difference, but it's worth looking at. It's a pretty clever concept. We've tried to make the task sharing a task in this context. I should define is an internal. Well, a job really is. A job is an internal task, such as matrix multiplication, where the user says, here's two 10,000 by 10,000 matrices, multiply them, and we'll split that up into 20 or so smaller sized multiplications and give them to the threads. The threads then have to contend with each other. The threads will be launched, they'll be woken up. They have to contend for access to the job control block before they can do their work. And so the amount of overhead that you spend where the threads are fighting over the job control information becomes important. Anyway, by using futexes, we have discovered that our internal jobs can be as short as 400 nanoseconds. Now, that's not very long. But even with jobs as short as 400 nanoseconds for each work unit, the amount of arbitration delay is negligible. So the mutexes tend to waste time as each thread has to go to sleep and wake up and grab the mutex and decide what to do. This futex implementation's got very low overhead, and I'm pleased with that. There's not a lot of processor or operating system overhead involved in switching tasks.
So a futex, is that something that would then, like when it finishes its task, it looks ahead to see if there's another task rather than shutting down?
The futex is just the problem. Okay, here's the problem with a mutex is you say, is there any work to do? No. Okay, then I'll wait. That's simple, right? The problem is, what happens if work comes in between the time you look to see if there's work and the time you wait? Okay, and that's just no way you can keep. That's a timing window that you can't close. So with a mutex, what you have to do is you say, oh, look for work. I don't think there's any work. Okay, let me grab the mutex. So I will seize control of the resource. Then I'll look again to see, did something come in? And if not, then I'll go wait. And part of the waiting is the system automatically releases the mutex. It means that if you have many, many threads, and processors are coming up with hundreds of cores now. If you have lots of threads, every one of them has to grab the mutex before it waits. And that's bad because it takes time. Anyway, the futex idea is really clever. Instead of using a mutex, there's a shared location in memory. And I look at that, so when I go to wait, I say, okay, what is that location in memory at now? Okay, when I read it, it was 300. And then my wait operation says, I'm going to wait, tell me when the value has changed from 300. That's just so clever. So now the operating system eventually gets control and says, oh, oh, he thought it was 300, but somebody's advanced it to 301. Whenever you add a unit of work, you increment the mutex, you see. And so there's no window. You don't have to grab the mutex. It's implied in the way the mutex works, and it's just more efficient. And we can measure the difference in the speed that heavily multitask jobs take.
And that's as a result of all the threads being able to look at the same memory. If they couldn't do that, you wouldn't be able to use a futex. Is that right?
That's right. That's right. It only works. Yeah, but the same thing's true in a mutex system. There has to be something shared. The mutex would have to be shared. Yes, but all you have to share is a single 4-byte value, and the operating system will avoid the overhead, which is good because it's a one time in a million that somebody actually does add a task after you look between the time you looked and waited. But 1 in a million is pretty often in the computer business. So you have to worry about it.
If I was going to use an analogy, if I said it was like sort of like a DMV or a hospital waiting room or something where that number's changing on the board, a mutex would be like you have to wake up the patient, point them at the number, and then put them to sleep again. And a futex is like everybody's looking at that number. Oh, it changed, right? Is that sort of the way it works?
I don't think so. I think an analogy could be made that's like that, but yeah, I don't exactly see how to do it.
Okay, well then just ignore what I said there because I just made up an analogy that doesn't work.
But that's a very good analogy. You come into the butcher shop and you say now serving 400,
right?
And you take a ticket. Well, with a mutex, I think you take a ticket and then see if 400. But with a futex, you just look up and see 400, and then you go say, I'm 400. Can you serve me? And usually the answer is yes, I can serve you. But the answer might be, no, somebody else came in and got 400 before you. You'll have to go back and check again. The point is that the case that has to be guarded against is rather expensive and extremely rare. And the futex avoids the overhead in that situation. Anyway, that's the first thing about this new J release, and probably the most important. Well, I don't know if it's most important, but it's big. It's something we've been thinking about for years. When should we go to multi-threading? And I think the processor vendors are telling us that now's the time. If a CPU has 100 threads and you can only use 100 cores and you can only use one of them, that's a hard sell to say that you're really taking advantage of the machine. The second big thing in this release is that the J extended precision math library has been switched from an internal one that we used to use to GMP, which seems to be one of the leaders in extended precision math. And it's just, it's more space efficient, it's faster, and for multiplication, it's way, way faster because it supports Fourier transform multiplication methods, which our internal version never did. That was Raoul Miller's work. I had no idea how hard that was going to be when we proposed it for work, but he stepped in and got it working. So anybody who wants to use extended precision in J will find that it is much faster than it used to be.
As an example, on the APL farm, I think it was actually last night, I was watching a discussion and somebody was trying to do a Rosetta code problem that involved extended precision primes. And they said, I got it working, takes about 2 or 3 minutes. And somebody else replied, well, really minutes or seconds? Or did you mean seconds? And they said, no, I meant minutes. And the person said, are you running 904? Are you running 903? Oh, I'm running 903. Oh, you should switch to 904 because what you just ran in 2 or 3 minutes took me under a second and a half.
Yeah, well, that's right. And if you're multiplying really big numbers, it could be thousands of times faster. It's great to have that. We don't have to be ashamed of our math library anymore. The third big thing, and actually the thing that will probably make the most difference to the average simple user, is that the error messages are much, much improved. Before, we'd have to say the error messages really sucked. You do something and you get domain error. That's all it is. Or length error. You did something wrong, but I'm not going to tell you what two lengths don't match. This is partly because of the way the J language is designed, and it might be true for any language that has significant amount of tacit programming. Say the parser encounters a hook. Say it's the hook that calculates an average, +/ sharp, +/ divide, count, tally, right? So three things. The first thing that happens is the parser parses the fork into an anonymous verb that takes the average. And then the parser launches that verb, and say the verb fails. There's no information in the verb that connects the failing verb to the token number, the word number in the sentence that caused the problem. And remember, with tacit verbs, you could have 24 primitives in this anonymous verb that's executed by the parser as a unit. So all we've been able to do in the past is say, we tried to execute this big thing and it failed somewhere and it had a length error. What we do now is we capture enough information at a low level that we can indicate which primitive actually failed. And then we take the arguments to that primitive and send it off to a J function whose job is to analyze this error. So there's a J verb. It's about 1,000 lines of code, and it knows what the different errors from the different primitives mean. And if it sees a length error, it can figure out what parts of the shape were supposed to match and didn't, and call those to your attention. So I think with one stroke, we've gone from having error messages that sucked to error messages that are pretty good. We'll see how the users like it, but it's a big point for usability, I think.
Does it make use of a lot of the, well, I shouldn't say newer languages. It is newer languages, but even older languages that are stealing this idea from newer languages. The caret, where it sort of creates like a little visual pointer to like point at the verb as well. Like it's a nicety, but like it's become almost the new languages that don't have it, people sort of raise their eyebrows and they're like, haven't you seen what everybody else is doing?
Everybody else, APL had this in 1966.
APL?
Yeah.
Yeah, we do it in some cases. Mostly what we do is we type the sentence in error and leave 3 spaces before the actual location of the error. In some cases, we print a caret. And if you're telling me that all the cool kids print a caret, I can go do that, because that's
I would probably do that, because I've always found that space display confusing. I mean, because like, what if there's spaces in the original function? Then you have to kind of line up and say where my spaces.
No,
it removes spaces from the display, right? But it's still, yeah. I've still found that confusing in the past. Where
okay, well, I'll put that in for 9.5. Because that would be trivial to do it, and we do it sometimes. Oh yeah, one good thing is that mismatched parentheses are
those are hard.
They're a problem, aren't they? Because you added a parenthesis and it just totally changes the way the system parses the sentence. So you'll get a spurious error indication. And with no hint, well, anyway, whenever we have an error like this, whenever we have an error, I scan the sentence to see if it has mismatched parentheses. And if it does, I'll report the error that the parser found, but I'll also say, and by the way, dude, you got a parenthesis mismatch over here. So, maybe you'd like to look at that first. So we can report 2 errors at once now in a sentence, where the parenthesis is probably the actual source of the error.
That one is fun in Dialog APL at least. You can have mismatched parentheses, and the interpreter will happily start executing the expression, and that might have effects before it hits the place where it just can't continue anymore.
Yeah, indeed.
So you can have
same thing in J.
And a partially evaluated expression that has mismatched parentheses.
Yeah, well, I was thinking, why shouldn't we scan the sentence for mismatched parentheses when the explicit definition is defined? Can it be right to have
maybe you leave the execution before you even hit that parenthesis?
Well, I just say fail the definition. I just tried to define a verb that contains a sentence with, it could be, I don't know. That would be.
Well, I can't imagine anybody complaining too much about their function that had mismatched parentheses, but it exited first, so they've never noticed the issue.
Welcome to the Python experience.
Yeah,
you write some code and it doesn't work, and we never executed that branch in my unit test, so we're gonna call it a day.
But once you get the error, it's awful easy to fix, especially if the interpreter is pointing out where it is.
But which parenthesis is the wrong one?
Yeah, that's the big problem. But I mean, that's just, there's no right answer to that. There's some nice heuristics.
Yeah, you can. All you can do is say this is mismatched, but you can't say.
But do you complain at definition time if the control structures are mismatched?
Yes.
So then it would make sense, the parentheses to that.
So there's precedent.
Yeah.
Yeah. Well, those are things to think about. It's nice to have work to do.
So what I'm wondering is, so now you saved information, so you can go in and see where you can see exactly the function in the train that caused the error. But what if it's what if it's defined somewhere else? Do you go to the place where that function is in the source code?
No.
So like if you have a function, if you have an operator maybe that takes in an argument that can be a number of functions, and you pass in the average function to it, and then you run it, and average is not too likely to get an error. But if you had a function that was tacit and did cause an error, like what would happen there?
The error is going to be reported on the source line. So let's say we have a tacit verb. Well, no, let's say we execute.
So it's the bottommost explicit source line.
Yes, it'll be the bottommost explicit. So the bottommost explicit source line. Let's say it has a hook that looks like parenthesis A space B space C parenthesis. So it's executing those three tacit verbs. If the failure is in C, you would get that line would fail with the error pointing to C, and the message saying error in whatever the primitive was. So you would have to, which might be in C, could be deep down in C.
Yeah, okay.
But it'll look at the arguments to the failing primitive and tell you what the primitive didn't like. And it's up to you to go from there. At that point, maybe you should turn on the debugger so you can go through the call stack and see.
Or just look at the definition of C.
Well, right, but C might be four more names that you can have a tacit definition that goes.
It could be an arbitrarily complicated tacit function. It just can't be in any explicit part of the function C. Yeah.
And that breaking down and looking at the arguments to something that fails, would that be available for something that didn't fail? Like, can we get access to that in the process? No.
The problem is executing a sentence. They're just oodles of places where primitives get executed. I would have to save all those results. And there's something special about the one that fails, right?
Right.
It's the last one, and it's the one you care about. But no, you.
But what are you asking for, Bob?
Well, I've been thinking for a long time some type of a visual debugger where you can see the structure of the verb and then go in and basically logic probe different areas and see what the arguments are. But as Henry points out, you have to have created all those arguments. It takes up a huge amount of space for what you're trying to do. But if you're trying to figure out a verb, it does give you a real leg up to trying to figure out what to go to.
Like dissect in real time.
Yeah, dissect does that.
But that only, it runs through everything and then gives you the analysis, right? You can't step
it's running it in its own mode, so it's got all sorts of extra overhead added. But if you're trying to figure out what the expression does, you probably don't care.
Right, that's the idea. Yeah, I mean, it executes every verb on every individual cell. Result cell goes into a table where it's kept track of. It's tremendous overhead.
Bob, have you seen the presentation from the Dyalog user meeting 22, where John Daintree does his token by token debugging?
No, I haven't yet.
Okay, so it sounds like something like that, and it should be coming. Probably not in the first coming version of Dyalog, but at some point, next one, where you can not just trace through statements, but you can go in primitive by primitive and inspect what arguments are they getting, what result are they giving, and then when you hit an error, you can see that as well.
Yeah, I'll have to take a look at that, because from what Henry's saying, when you put together a fork or a train, you've created a new verb. You don't think of it as the individual parts. It's now a new verb that does the thing. And using the tokens, you're breaking it back up apart. And I don't know. That's the trick, is between those two levels of understanding.
But for analyzing what's going wrong, or why you're getting a result that you're not expecting, or for learning purposes, I think it's tremendously useful to be able to follow along as the interpreter traverses this function tree and runs it.
Yeah, I actually did a promo video. I built the whole thing out of Keynote. It doesn't actually, it looks like it's working, but I'll put it in the show notes. It's a video of what I kind of think would work, and you just, with a mouse, you go around different parts and you can see the structure of the verb and tell what's happening, and it's kind of cool. I haven't put it into place yet, but it sounds similar to what John's doing.
All right, I think actually don't know. I think we passed the hour mark. It's hard to tell when you hit the record button, but is there anything that we haven't mentioned in terms of, primitives that were added, or that's worth mentioning before we?
What is use? What is slash dot?
I think slash dot was incorrectly defined. I think in Dyalog you did it right. That's one of those examples of waiting till somebody else does it wrong first.
That's key?
Key, yes.
Yeah.
Key. What key does is it classifies the items of the right argument based on the values in the left argument. So subsets of the right argument that have identical values of the left argument are grouped together, and the verb is applied to them. You would think that the correct definition would be make that verb dyadic and let the left argument be the left argument value that they all have in common, and the right argument value would be the subset of items to be operated on, which I think is what Dyalog does. But it was not defined that way. It was just it just throws away the information in the left argument to key. So this slash dot dot merely, it's just like key, except it executes the verb as a dyad and gives it
another left argument.
Yeah, gives it a left argument. So if the left argument is a bunch of fathers' names and the right argument is a bunch of children's names, you might want to say, well, who are all the children? Let's connect the fathers to the children. With the old-fashioned key, you'd get the children's names, but you wouldn't have the father's name. You'd have to come up with that by some other means.
So you had to take you basically would be forced to, I guess, box and then doing each. Yeah. So yes, exactly. And so this is just an improvement. I have wanted to have it half a dozen times in 30 years, but I think it's just properly defined this way. It's interesting because I think key was added to Dyalog APL just before I joined the company, and I know that there was Roger was implementing that.
Right. Yeah.
And saying that they're fixing the issues with J's key. So
Yes.
so yes, that's exactly the thing. Although Dyalog probably waited like 15 years or something after J got it until it was added to the language.
Yeah.
But actually, I have a different problem with key, and which is when it does what I want it to do, then yes, it does it really well. But often I have a vocabulary that I want to look at. So let's say I want to use key to do letter frequencies. Then if I just do key, then they have two issues. One is if any letter doesn't appear, then I don't get a frequency of 0, or count of 0 on it. It just doesn't appear in the result.
Yeah.
And another one is that it includes things I don't want to count, punctuation and so on.
Well, you could throw those away when it's over, right? What's normally done to get rid of the missing letter problem is you take your whole alphabet and prepend it to the text so that everything appears at least once, and then subtract 1 from the count.
That's both awkward and potentially very expensive.
Right. Well, okay. Append it to the end of the text, and it might append in place. It will in J. I don't know about Dyalog.
But then you need to sort after that.
Yeah, because there's also an ordering problem.
Yeah. If you put it at the end, then they will appear in whichever order they appeared in the input. If you put them in the beginning, they will now be sorted according to the alphabet.
Okay. Yeah. I guess it depends on what you want.
Right. But then you have to sort afterwards, and as well, it can also be expensive. So I was just curious, adding a new key, but not fixing those issues. Yeah, time for / or something.
I haven't seen those as issues much, but those are the high spots. There are numerous performance improvements, but nothing to compare with threads and GIMP and the error messages.
Well, we'll leave we always do this, but we'll leave a link in the show notes to the change log, or I think there's a
release notes.
Yeah, release notes that document everything that's changed. And I guess sort of the last thing, and maybe the most important thing to ask, is this available? Because I think I looked it up, and right now I think the J software wiki still points to the beta.
It was supposed to go out yesterday. I just got an email from Chris that it's all working except the Mac installation. There are no changes to the interpreter. The problem is this damn change to the numbering system. So something breaks because it's not 9.04 anymore. It's 9.4. It will be out before this podcast is released, I'm sure.
I was going to say, is the yesterday for us is like 5 days ago for the listener. So hopefully by the time the listener's listening to this, 9.4.1.
I feel certain it will be out.
Awesome.
We'll leave a link to the download page.
Yeah. This is like time travel happening right now. It's currently for us, it's not available, but for the listener listening to this right now, it is.
That's true.
Well, it's available as a beta, right?
Yeah,
this is true. Yeah.
It's the same as the beta.
It'll be the same as
no
beta.
changes since the last beta.
But I wasn't able to download the beta either because a broken link for it.
Uh-oh.
Probably because of the name of things.
Dun, dun, dun.
Yeah, that was a nightmare. I hope it's worthwhile. I think it will be.
All right. Well, this has been awesome. I'm definitely going to have to. Well, actually, I don't, because I got a new OS. I don't actually have J locally right now. So I've been using J Playground for the last couple days or couple weeks. But I'll have to go and download this 9.4.1 to mess around with the tasks and see how much trouble I can get myself into.
Well, that would be great.
I was going to say, that's a good question. Would J Playground update to 9.4?
That is, I don't have anything to do with J Playground.
Yeah.
It's I'm in awe of the project.
Probably the person that works on it is listening right now. And they're thinking,
Joe,
yes, it definitely will be updated. So, and if they're not thinking that, well, I just basically put those words into your mouth. And so now you need to go make it happen.
We'll see how busy Joe is, but there wouldn't be anything in 9.04 that would, or 9.4 that would keep Joe from using that source, would there?
Not that I know of.
Okay.
We try to run on everything back to 32-bit Raspberry Pi. Well, actually, multi-threading doesn't work on that.
Yeah, that's what I was about to say. But hold on, the J Playground that is compiled to WebAssembly, right? Running in the browser. How do you spin up OS threads in a browser?
I don't know. These are POSIX threads.
I mean, I feel like if you're running J in the browser, probably you're not in a situation where like the fact that you can't spin up, 12 different threads for your computation. I mean, I think if you're at the point where you need to spin up threads to get like a perf increase, maybe think about downloading the actual executable.
I have this coming up all the time about try-APL. People are trying to like write, I don't know, production applications or something running on.
Yeah, I did get a YouTube comment the other day that said, I do most of my... They said that they found try-APL better than ride, which I was kind of shocked by because there is a certain amount of latency with try-APL. Like, it's not terrible, but when you're used to like the hit a button and it's instantly there, I mean, for what it's worth, I actually did use try-APL for maybe like half a year or something until I finally went and downloaded one of the editors. So maybe they're just at that point as well. But at a certain point, you start doing a certain amount of work that the latency, once you switch to it or try it out once, you're never going back. That being said, now that we're talking, I'm rambling on about this, BQMPad, I think I religiously use. At one point, back when I had Linux, I did install the BQN executable or CBQN just to try out the little color syntax highlighting, because that we announced that, or Marshall announced that at some point, and it was awesome because like J does not have that. If you're running J on Linux, or I think actually even if you have like the little GUI thing on Windows, it doesn't have sort of like inline syntax highlighting. And
you can do that. You can do that by going in and you can do that in JQT by editing your styles.
The default style is just...
This is in the terminal though.
Oh yeah, not in the terminal, but in the IDE in JQT.
Okay.
You can go in and edit. You can configure your style, and then you just have to go into your. I think you have to go into your base and then actually enable inline. But when you do those two things, you can convert to whatever colors you want.
So I guess on Windows, if you're using JQT, you can set it up. It's not by default. But on the terminal one, which is typically what I would use when I'm on Linux. And there's only actually like a few interpreters. Like there's IPython, Elixir has one called IEX that has syntax highlighting. I'm sure there's a Haskell one, although the default one, GHCI, does not, and then BQN. So like off the top of my head, of the languages that I've used, like only a couple of them have it. And it is like, I don't know, it doesn't really matter, but when you're used to being in like, VS Code or choose your editor of choice, like the syntax highlighting is actually a part of like, parsing and being able to read. Anyways, point being, these online playgrounds and try-APL and BQMPad. All right, this was the last 30 seconds of my monologue. Every other language should go and do something similar to BQMPad, because I had someone comment that on a YouTube video the other day too, is that like the in-place updating, where like you don't see the iteration of every sort of modification when you're building up some solution. What was it? Was it Stephen Apter? Was it Joel Kaplan that said, solutions by successive approximations or something like that, which was, anyways, a great quote, is that I just like, I don't actually want to see the iterations. I just want to like add a tally to the front and then see it go down to a single number and then add something, which is like BQMPad has both. You can hit Shift Enter to get the iterations if you want to see it. But if you don't, and it's specifically, maybe I'm biased because I make YouTube videos, but for a YouTube video, it's absolutely beautiful because like you're just building it up, your screen doesn't move, and then your solutions just like spit out to the screen. And it's like, I'm sure Andre Pop or the folks that work on it weren't thinking of like content creators, but it's like the perfect, like they went and built this thing and I'm just like, oh, this is awesome. Anyways, there's my, I guess that's the third thing that I've sort of put out into the world and asking people to create for me without actually doing any work myself. But
now this is one place where the language semantics are really important because so BQN does this without, at least we've tried to do it. There are probably, bugs in one or two places, but it does it without ever messing up your previous results. So the results you get are always consistent with if you had just typed it that way in the first place, even though it's evaluated your statement and done a preview. It can't always do that. So like in places where you modify a variable that's at the top level scope, then it can't do that. But in most BQN programming, you don't actually end up doing anything like that. So it can actually keep track of, what's supposed to be where, and then throw out the changes it makes that it made while doing the expression. So it handles a whole lot of code without without having a bunch of messy modifications and imperative stuff that it has to go back over and undo.
I still don't understand how that you can actually do that when you do change values of variables in the global scope. How does it not? Every time you modify the line.
So it actually makes a new scope for itself to.
It makes a temporary scope or clones the scope for every time, so it doesn't affect it over and over again.
Yeah, and of course, any function that it calls is going to execute in its own scope. So once the function's done, the scope disappears, and usually, and so that it can just throw out. So basically, it's the main mode of operations is that it's making space for itself to put these temporary results, and then at the end it just throws it out instead of trying to undo any changes it made, because that's really error prone.
Okay, so just by cloning the scope.
Look at this. Adam's already working on it in his head. Fantastic. And the beautiful thing about this is that,
but it's very important that it has this very clean lexical scoping model for that. So not every I think they have it in JavaScript, but it's taken a huge amount of effort to support that, and they've gradually extended it to more kinds of things. Even though JavaScript has lexical scoping, it's just that more features in the language makes it much harder to do.
Yeah. The cases that I really care about too are not the complicated ones. It's just like the single sort of expressions with a couple unit tests. And the thing I was going to say too is this helps with the issue of not knowing how to get the previous line. Like in J Playground, I actually don't know how, because in Ride, it's Control Shift Backspace. In BQN, I don't know, it's Control something, but I didn't know in BQN Pad because I'm always just modifying it in place. But in J Playground, I don't know, I always just have to hit the up arrow and modify it, hit enter. I don't know how to get the previous line to show up on my new, and for the longest time in Ride, I didn't, it's a 3-character shortcut. I was always just doing the old thing until one day, I saw some YouTube video by Adám, and he spelled it out, because not all the times are you spelling out. I don't know. Bob is furiously trying to type to figure out what it is.
I'm giving away all my tricks here.
The thing is that I love these languages and I can never remember. But the beautiful thing with BQMPad, it's only one of many beautiful things. It's I don't have to remember. I just start typing, keep going. Anyways, we're holding Henry hostage here, doing an entire different episode.
It's Control Shift Up Arrow.
Yeah, there you go. So another 3 combination, Control Shift Up Arrow. Good to know.
Yeah.
Anyways, we'll wrap up this lightning talk at the end of our episode with Henry. Thanks so much for coming on, Henry, and telling us all about this. And listener, check the show notes, or just go to JSoftware, and you can find the links to download this and to look at the release notes for anything that we may have not mentioned today. Bob, people can reach us at
contact@arraycast.com. And we actually did get a reply from Daniel. We mentioned him in the last letter. He was very touched by our information.
Uh-oh. We're in a recursive infinite loop here now.
Yeah. But he said, don't worry about giving away. He says there are several Daniels involved with Clojure development, so he's not too worried about you giving away his identity there.
Awesome. And we didn't get to, we had on the back burner a topic of J folds, which is the capital F suffixed by either a combination of a dot or a colon. We will have Henry back in the future. Maybe not next episode, but in the next few episodes, because it's something I was looking at, and I think the listeners would be interested to hear that conversation. So if you're willing, Henry, we'll have you back and hold you hostage once again.
Would love to.
All right. I guess with that, we'll say happy array programming.
Happy array programming.